computer. Cool. Share my screen. Can everyone see the R code set up?
Yep.
Cool. So yeah, today we're going to do a quick demonstration of agent-based modeling in R. We're going to do two models. The first one is going to be a simulation recreating Schelling's model of segregation. Also, sorry, is there a weird reverb on my headphones? No? Yes, a little bit? Okay. Sorry to the people who are watching this later and maybe getting, oh, it stopped.
I think
Great.
it's gone. I think it's gone
Okay,
now.
cool. Um, so the first one's going to be a recreation of Schelling's model of segregation, and the other one is going to use sort of just made up data, but we're going to pretend that it's real to learn how to initiate an agent-based model with real empirical data. Or in our case, hypothetically real empirical data. But so first, just as a quick refresher, agent-based models are computational simulations that model the behavior and interactions of agents within a system. These agents can represent people, organizations, or other entities, each with their own characteristics, rules, and decision-making processes. If you want to program them down to that level, of course, all agents could just follow the same set of rules. By simulating the actions and interactions of these agents at the micro level, researchers can observe emergent patterns and phenomena at the macro level. That is basically summarizing my whole hour-long presentation from a few months ago. I could have just said that and been done with it. But what are the components of agent-based models? First, agent-based models consist of environments in which there are the agents, individual entities with unique attributes and behaviors. These agents interact with each other and their environment based on defined rules. Then there's emergence. Complex system level patterns arise from simple agent level rules and interactions. There's also agent-based models are flexible. ABMs can incorporate heterogeneous agents and adapt to changing conditions. For instance, an agent-based model could focus on the spread of social norms or behaviors within a population, or it may simulate the adoption of a new technology or cultural practice. Individual agents could have different characteristics like age, social influence, and openness to new ideas. The rules governing their interactions might include the likelihood of adopting new behaviors based on factors such as the proportion of their social contacts who have already adopted it, the perceived benefits of the behavior, and their individual resistance to change. So very, very flexible, very adaptive models to sort of whatever you want to create so long as you're observing emergent phenomena. As the simulation progresses, the model can showcase how the new behavior spreads through the social network, revealing patterns of early adopters, late adopters, and non-adopters. This can provide insights into the role of social influence, network structure, individual characteristics in shaping the diffusion of innovations or cultural practices within a society. By testing different scenarios and interventions, researchers can identify key leverage points for facilitating or inhibiting the spread of specific behaviors or norms. I also realized that might have been slightly confusing because I had changed the prompt or the premise for that example and then forgot to delete a sentence. So at the beginning, if you're confused why I switched the topics, that is why. But how can ABMs be applied in social sciences? Well, first, social networks. ABMs can simulate the formation and evolution of social networks, studying phenomena like information diffusion, opinion dynamics, and social influence. So stochastic actor-oriented models are examples of social network models that use agent-based modeling. Collective behavior. Researchers use ABMs to study how individual behaviors lead to collective outcomes, of course, so emergent phenomena such as crowd dynamics, segregation patterns, or the spread of social norms. In economics, ABM can model economic systems, including market dynamics, financial markets, and the effects of policies on individual decision-making and overall economic outcomes. In public health, ABMs are used to study the spread of diseases, evaluate intervention strategies, and model the impact of health policies on populations. In urban planning, ABMs can simulate urban growth, traffic patterns, and the effects of land use policies on city dynamics and individual behavior. By providing a bottom-up approach to modeling complex systems, agent-based models offer valuable insights into the mechanisms underlying social phenomena and can help researchers and policymakers better understand and predict the effects of interventions on these systems. Now we'll get into the actual coding part. So first, you can do agent-based models just in base R, which is what I did here. So I don't actually have any packages, specifically none for agent-based modeling installed. There are a few, but I found that some of them were not up to date. Some were sort of confusing. So I just stuck with making them in base R here. The only packages here, ggplot2 and dplyr, are just sort of data visualization, data management packages, nothing that is necessary to create an ABM. So like I said, for this first part, we're going to recreate Schelling's model of segregation. It's one of the most famous applications of agent-based modeling in social sciences. And it sort of basically this economist named Thomas Schelling in the 70s showed how individual preferences for neighbors and when simulated can lead to significant segregation, even when the preferences are relatively mild. So I believe he says between people within a neighborhood who have a preference for similar neighbors along whatever trait. So for instance, race of like 0.3 to 0.5 within a neighborhood can lead to near total segregation. This is an example of a theoretical application of an ABM. So he's not drawing from empirical data here. He's sort of testing theoretical levels or theoretical situations in which segregation can occur. So first, like I mentioned, ABMs rely on an environment, or oftentimes, I guess you could just have actors interacting with one another without a specific environment created to visualize it, but there's some sort of environment that you're imagining is there. So this first part creates the environment. So you have the grid size. We're going to create a 50 by 50 grid. The empty ratio, so what percentage of spaces in the grid are actually empty, so 10% here. What percentage of spaces in the grid are going to have type A agents? So you can imagine that type A and type B agents here correspond to any particular social trait. So obviously with Schelling, it was meant to represent race. So 45% of the initial grid is filled with type A agents, 45% is filled with type B agents, 90% total, 10% empty spaces, because people need to be able to move. So we're going to imagine that this is a neighborhood. And then we set the seed, so here to be able to recreate the code, make sure that it's, or recreate the results, so make sure that the results are reproducible. Did 1, 2, 4 because I tried 1, 2, 3 and it actually was not very pretty, and 1, 2, 4 worked better. So that's why it is 1, 2, 4. And then this line creates the actual grid here. So the sample function is used to randomly select elements from the vector C, which is A, B, empty, which represents the possible states of each cell in the grid, occupied by type A, occupied by type B, or empty. Grid size squared calculates the total number of cells in the grid, so it's 50 by 50, so 2500. Replace equals true allows for the same elements to be chosen more than once, essential for filling all 2500 cells. And probability equals C ratio, B ratio, empty ratio sets the probability for each type of cell, ensuring the grid is filled according to the specified ratios. So we'll do that now. You can't see it, but we have a grid. We have an environment. And now we're going to examine that environment. So we load a visualization package here. And then we're going to plot the grid. So this line starts the definition of a function named plot grid. The function takes one argument grid, which is expected to be a matrix representing Schelling's model of segregation with cells containing A, B, or empty. And then this basically creates this function with which you are just using, it's just a shortcut to use. Oh, sorry, Will, I just saw you had a question.
Yeah, could you show what the grid looks like? Like if you just turn it into a matrix as it is now and then just like view it? I was kind of curious, what is it just like?
Yeah, sure. So can you see it?
Yeah.
Yeah, so right here you can see it is, yeah, essentially a matrix of just A's and B's and empties across 50 by 50, or across 50 rows, 50 columns, randomly placed. Is that what you wanted? Yeah, good, cool. Now we're going to actually visualize it, make it look a bit prettier than just some rows and columns. Here we go. Here's a grid showing the matrix here, turning it into pretty visualization with colors. You can see that the grid does not start out segregated at all. So if you're imagining this as a neighborhood, you're seeing a random, totally random placement of these two different groups of people throughout the neighborhood. There's no discernible pattern at face value to how these people are placed. There's no evidence of segregation in the initial environment. Now we're going to set the behaviors for the agents within the environment. So threshold here is going to set the threshold of like neighbors below which agents are going to move. So in the context of Schelling's model, this threshold represents the minimum proportion of neighboring agents that must be of the same type as the current agent for the agent to stay put. If fewer than 30% of an agent's immediate neighbors are of the same type, the agent will consider moving. This is the function that actually defines the behavior. So this, it's labeled this on my notes, sorry. But basically, this is retrieving the number of rows in the grid. Since the grid is a square, this also represents the number of columns used to control loops that iterate over grid positions. Require empty finds all positions in the grid where the cell is empty. And this parameter here ensures that the positions are returned as matrix indices, which are necessary for locating empty cells where agents can move. And then these lines start nested for loops to iterate over each cell in the grid, with X representing rows and Y representing columns. This condition checks if the current cell is occupied by an agent A or B. Neighbors retrieves a submatrix of the grid surrounding the current cell, including the cell itself, representing their local neighborhood, local part of the neighborhood. The use of max and min ensures that the boundaries do not extend outside the grid. And then like neighbors counts how many cells and neighbors are of the same type as the current cell. Subtracting 1 removes the current cell itself from the count. So that's why we have the -1 here. And then this block here is going to handle the actual movement. So checks if there are any empty spaces available. So if the amount of neighbors is below, if the amount of like neighbors is below a threshold, then if there are empty spaces for which an agent can move, it will move the agent to a new empty cell. It sets the original cell to empty. So that's what this line does. And then it updates the require empty to reflect this change, adding the original cell to the list of empty cells and removing the new cell from that list. And then it returns the grid. So that. This has not actually changed anything in the environment so far. This was just defining the function which creates the behavior for the agents. And finally, we're going to run the model. So this for loop says for 10 iterations for the grid, move the agents based on the behavior that we've described, and then show us what the grid looks like. So let's look at the original grid here. See, let's remember it for comparison in a second. Run this, it's doing the iterations, and then it's going to show us what it looks like. So our neighborhood has now obviously become much more segregated with a relatively low preference threshold. We see, much more cohesive in terms of traits of this one, trait of A or B, much more cohesive local blocks. There seems to be many more people, or like there seems to be much just overall greater segregation between the groups, but it's not as much as Schelling's original model indicated because it only ran for 10 iterations. So what we're going to do now is first we're going to increase the threshold to 50%. So we're going to say we're going to have pickier agents here. They want 50% of the people around them to be at least 50% to be the same as them. And then, sorry, trying to find my notes here. Okay, yeah, and so then we recreate the function here. Basically, I was having some trouble with this when I was originally setting it up, and I was recreating the behavior function to track changes in the movement because it was not moving for some reason. And then I fixed it, but really this is the same function as before, just with some troubleshooting steps added in to tell me what was actually happening. So let's define this again, but really the only part that matters here is the increased threshold. So now that we've increased the threshold, agents are going to move differently. Iteration 0. Okay, so now we're going to make it so that this version, instead of running 10 iterations, is going to run until the agents no longer want to move, or until 100 iterations have occurred, because we don't want it to just run forever. Theoretically, it shouldn't just run forever. Like agents should reach like a stable place, and they do. Knowing from how this is going to run, they do very quickly. But just in case there is an error with the code and the simulation never reached a stable state, then we put the 100 in there to make sure that they are it's not just running forever. And so moves made true is just did any agents move in the last iterations? How many iterations have there been? Well, agents are still moving around, and while the iterations is less than 100, move the agents, create the grid. Oh, sorry, my roommates were saying something. And track the amount of iterations that are taking place, and then plot the grid. So if we run it now, we see a much more defined segregated neighborhood. And the agents took 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, blah, 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 about like 20 iterations to reach that level of segregation where they reached a stable state. So you see sort of the secondary neighborhood here as compared to the final, much more segregated neighborhood with only a preference for half of your neighborhoods or half of your local neighbors being the same as you along this particular trait. You see extreme levels of segregation within this neighborhood, recreating Schelling's model. Any questions on this first part? Yeah, all made sense.
Yeah, it was pretty clear. It's pretty cool.
Okay. All right, and so then for this next part, some water real quick. We are going to ground an ABM in real world data, in our case, hypothetical data, to try and capture the complexities of human behavior and social dynamics within an agent-based model itself, potentially leading to more accurate predictions and insights. The Schelling's model was a totally hypothetical situation, right? So he's trying to discover, like what hypothetical degree of neighborhood agent preference for similar neighbors would you need to create a segregated neighborhood? And so he finds it's very low. It's much lower than you'd expect. But you can also use ABMs with real world data. And so here, we're just going to create a simple sort of demographic data set. This, again, set the C for reproducibility. This time, 1, 2, 3 worked perfectly fine. And then we create a data set of 500 individuals where they have an ID number, so 1 through 500. They get an age randomly between the ages of 18 and 70. They get a sex variable, so male or female. And then probability, we'll do 50-50. I know technically male and female, you are slightly more likely to be male than female or assigned male at birth than female at birth. It's like 51%, 49%, and then it lowers over time. And then there's probably more females or women in the population in 18 to 70, but we'll just say 50-50. And then we're going to simulate a income for them. So we create an income distribution where the mean is 50,000, standard deviation is 15,000. We're going to assign each person a random income. There's probably going to be some very rich 18-year-olds randomly in this sample population. Then we're going to assign them a random education level. So high school, bachelor's, master's, PhD, and then the likelihood of them having each. So 40% have only a high school degree, 30% will have a bachelor's degree, 20% will have a master's, and 10% PhD. And we can preview this data. So the first person is a 48-year-old male with an income of $45,000 who just has a high school education. That's pretty good for just having a high school education. It's beating the 32-year-old male right below him who's making less than him with a bachelor's degree. Interestingly, then there's a 68-year-old master's. This is sort of matching up with what you'd expect from income, age, and like education levels in terms of the patterns here, but it is totally random. And I'm sure if you kept looking, then you'd have some weird outliers of like, again, an 18-year-old who's making $100,000 with a PhD. So we want to model the decision-making process of these individuals regarding participation in a local recycling initiative. So imagine that you're some sort of like, oh yeah, Frankie, you raised your hand.
Yeah, real question. I imagine you can, instead of just doing randomly, you can set up a like average distribution or like a code of like a regression of if you assign one category, what likelihood of the future one to be like, oh, if you have high school, then you're more likely to be making more money or something like that. Okay.
Oh yeah, sure. Yeah, no, you could definitely do something like that. I guess technically what I'm supposed to be simulating is using real world data. So ideally you would just have, a data set that actually has all this stuff in it already. But I didn't want to deal with like finding a data set and then cleaning it up. So I was like, I'm just going to make this hypothetical data set.
Yeah, I was thinking mostly if you do like somewhere like in between where you have some part of the data set that you know, but there's some that you're simulating based on like where you make a simulated data that is educated by things that you know, like salary for men and women, we know that there's a gap. So like, oh, if it's a woman, then the average salary would be based on this. If it's a woman, average salary based on this. If you're like simulating following like trends in real data to still simulate non-existent data.
Oh yeah, absolutely. Yeah, no, that's a great point. Like you said, incorporating something like the gender wage gap to see if that in your simulated data set to see if that's going to, or the data set you're using for the simulation to see if that's going to affect outcomes in a way that you would find interesting. Yeah, for sure. And then, so like I said, imagine that you are, like a local politician. You want to know, will people adopt this recycling initiative? I am predicting, I guess local politicians are never going to do something like this, but they predict that the decision to participate is going to be influenced by these sort of personal characteristics, so age, sex, income, education, and the behavior of your neighbors, right? So have over here, just add initial participation status, we have a number, which is the number of rows for people. I think this is referring to, I didn't write this down. I think this is referring to the first free people. No. Referring to the number of variables corresponding to, or number of people just in the data set, sorry, it's rows. And then we're going to define income brackets, or take the data that we have. We're going to sort of create these income brackets of low, medium, high, very high. So we're going to say that people who have between $0 and $30,000 for their income have low income, 30,000, 60,000, medium, etc. So $90,000 to infinity is very high. And then we're going to create a social network based on similar education and income brackets. So let's imagine that we are assuming that people in this town are friends with people who have similar education levels, similar income levels. You can imagine this is just representing like the jobs that they're doing in the town. So we're creating a little social network here that is connections between people in the town, education level, income bracket, find peers with similar education levels and income brackets. If there's a certain degree of similarity, then identify that they are similar. Else return that, or if length is similar, return. Let me find this, sorry. ID peers from their personal connection. So what was I doing here? But yeah, basically creating a social network based on people who have these similar characteristics. And then we're going to make a decision function that will determine whether they are going to participate in this recycling initiative. So for instance, let's see. Sorry, I lost my page here. Yes, so for each person, you want, here it is. Okay, it updates each agent's decision on whether to participate. So we're assuming that their initial participation status is false. So it updates their decision to participate on whether they are have peers who are willing to participate, and then also based on their personal inclination toward participation based on their income and education levels. So there's a baseline personal inclination, and then we are assuming that people with higher education levels are more likely to participate, and people with higher income levels are less likely to participate. And then the, sorry, it's mixed up because my initial one, when I did this, like did one iteration and then finished, and I wanted to make sure that the thresholds were lower for creating, so my notes are a bit all over the place. But basically, it's going to create a final sort of decision likelihood here based on their personal inclination, the influence of their peers, and whether they reach the decision threshold that we've set in the model. Then we create a vector here to store participation rates, and then we actually run the simulation. So over 10 iterations, we're going to see whether people end up taking the or adopting this, and then we'll see what the average or participation rate, or what percentage of the population here actually participated in the recycling program that we set up. So we run it. Oh, R encountered a fatal error. The session was terminated. Whoops. Are you all seeing that? Okay, let's pause the recording. All right, we're back. Sorry for the technical and personal errors here. So let's just run everything that set up. Sorry, it's got to run all the old models beforehand. So basically, this is showing that at the end, 89.4% of individuals in our data decided to uptake the recycling initiative based on the parameters that we described. However, if we want to actually visualize this, we can when it's running the data, store the current participation levels. So that's basically what this for loop is doing here. This was, again, for debugging purposes, making sure that the participation rates were not immediately going to 100% the first time I constructed this. And then we're going to visualize it in a line chart here. So you can see, based on the parameters described, after we can say this is weeks. So, after around 1 week, or we start with an initial participation rate of around like 35%, which was, so technically when we initiated it, it was nobody was participating in the initiative, but then we said, if based on your education and income levels, you might be an initial adopter of this, regardless of peer influence. So around like 35% of people in the initial simulation are taking on this recycling initiative. Then after about 1 week or so, you get around 55%. Close to 2 weeks, you get already up to 75%. 3 weeks, you're almost at 90%. And then you sort of hit this plateau right around, let's see, it's 2.5 there. So this is actually right after 3.5 weeks or something. It plateaus at this 89.4%. We see that in future weeks, not likely to increase at all due to the nature of the data that we've constructed and the parameters that we've defined. So that is essentially how you can use empirical data to initiate your own agent-based model. So you take the initial sort of conditions, you construct the behaviors based on what you expect to be, what you're expecting. Could be drawing from personal experience, could be drawing from prior research on something. And then you run the model with this intervention to see what happens. And here we see very quickly, within a matter of weeks in this experiment, people uptake this recycling initiative based on peer influence and their own personal attributes, and that it plateaus around 90% of the population in this data set, which matches, I guess what we would, what we know about data on peer influence in social networks and the spread of behaviors in social networks. So, be right back, hungry hat yelling. Yeah, that's all I have for today. Any questions on anything? Thank you, Will. Apologies for the rough explanation in the second part there. I realized I did not update some of my notes for the when I redid the behavior parameters because the initial one, like I said, just went from 0 participation to 100% participation within 1 week, and I was like, all right, let's see what's going on under the hood here.
Yeah, no, that was really cool. I also really liked how also you showed 2 different examples of how you can measure the outcome you're focusing on, where it was visually to see the segregation, or here where you're just like, oh, what is the total percentage of people that are taking up and participating in this initiative? So it just shows like flexibility on how you can organize it based on how you define things.
Oh, thank you. Yeah, no, that's a great point. Yeah, there's tons of different ways that you could visualize data or just extract the information that you're looking for from the agent-based model. So yeah, here we're interested in what percentage of people said were adopting this, and so we got that initially, and then we were like, okay, but how, like, what is like the trend here? Like, are we actually going to see an increase if we ran more than 10 iterations? And it seems like no, it just sort of stops at around this 90% threshold. So different types of visualization can reveal different things, different emergent phenomena within the models.
Mm-hmm.
Anything else? No
I guess the only
worries.
question is, did you try Net Logo at all, or were you just like, no, I'm going with R straight because that's the world I live in?
Yeah, I just ended up going with R based after I talked to Scott, because I said, oh, I'm having some troubles with these packages. Like, do you have any recommendations? Because there's a net logo in our package,
Oh, okay.
and he was like, "Oh, just use base R." He's like, "Can you just do everything in base R?" He's like, "You don't have to bother with the packages." So I was like, "All right,
I guess
I'll try that."
this way you know exactly what you're doing, and there's nothing in the background doing weird stuff that you don't know.
Exactly, exactly.
That's cool.
Thank you, Will. Thanks, Frankie. Thanks, Jenna. Thanks everyone for coming, taking time. I know
Ah,
it's I just thanks everyone for coming. I know that it's a rough time in the semester for well,
yeah.
based on the uh, things happening on campus and grading and such. So
Just last question. Would
yeah,
you make this code available so we can take a look at it in our time if we want and try to figure out how it
sure,
applies to Smooth?
sure, yeah. I'll set up a GitHub page, and I know Todd had one set up for the workshop already, so maybe I can ask him if I
Okay.
can just take his old one and then use it, or at least copy his old files because he has some great demonstrations in there. I think he recorded some
Awesome.
great ones that Will did 2 years ago. So yeah, having those old demonstrations will also be really useful for everyone. So yeah, and we'll upload the recording there and the code. So,
Awesome. Great. Thanks, man.
okay. All right. That's all. Good luck with everything, everyone.
Oh, one quick thing.
Oh,
Any
one quick thing.
plans for next year, I guess? Next academic year?
We'll see what people want. You know, it's sort of whatever people are interested in. We had, I guess, an agent-based model theme for this semester. Um, and so, you know,
I can't
um,
tell you hairball. I'll be back in it was a good presentation.
you're good. See you later.
Yeah. So
Um, but yeah, if whatever people are interested in, we can do. We could. I know it's been enough years since the first round of this workshop that we could go back to some of the stuff we covered first year. Uh, show it again for new people. Build on it. See what's changed in the field. So yeah, but if you all
awesome.
have any suggestions, feel free to let me and Scott know.
Sounds good. All right. Have
All
a
right.
great weekend.
Yep. See you later, everyone.